Okay, so we're going to start the lecture on bearing. Okay, and the first part of this lecture is PowerPoint. Basically, I'll give you a brief introduction to bearing, and then we'll look at how we design for bearing. Okay, and so basically it's a selection of bearing, not really design. So the objective is to be able to identify different kind of bearing types. Okay, so we learn what they look like and what are their applications. Develop an understanding of the reliability, loading, and life of bearing and how they are related. This is basically the part, the calculation part. So you have a catalog, and the question is which bearing shall we select, or which bearing shall we choose? The decision should be based on the calculation of current loadings and desired life of the bearing. Okay, so that's the second part here. To study selection procedure of different type bearings. So basically, we're mostly what focus on is the ball bearing, okay, deep groove ball bearing, and roller bearing. Okay. So looking at this chart here, and we're not going too far. We're still here. Okay. Still here. So 10,000 years ago, our ancestors find rolling provide better speed than sliding. And 2000 BC, and this Egyptian find that using rolling to build this pyramid, right? And now in 2000, we have this sophisticated and high precision of roller bearings and other type of bearings, okay, to provide smooth motion for support of different kind of components. Okay, so manufacturing of bearing is a very precision process. Here's some of the anatomy of or terminologies associated with the bearing. When you look at the bearing, there's always two rings. One's called inner ring, the other called the outer ring here. Okay, the balls sitting between the inner ring and the outer ring, and they're actually sitting on a so-called groove or the track. So we call the raceway. So this is basically the raceway for the ball here. Okay. And the ball are normally sitting in the cage. So they're cage around here. Okay, so it's the cage for the balls. And some other dimensions, important dimension when you look at the catalog or when you specifying a bearing is the so-called ball size. So that's the inner diameter, okay, at here. So that's the ball. And one more important parameter is called outside diameter. Okay, so it's basically how high it is going to be. So this is actually also important because you're going to mount everything in a gearbox. So this dimension sometimes restrict that how much that the gearbox, how much the size of the gearbox should be, right? So similarly, the width, right, is also part of the dimension here. So when you design for shaft, right, the length of the shaft has to take this width of the bearing into consideration there, right? So those are basically some important parameters. There are some other important thing is the corner at here. Those are basically corner radius. Okay, so similar to the corner radius here. So those radius are in general will be given in the catalog. Okay, yeah. So this is basically a simple anatomy of the bearing. Okay. What do we use the bearing for? So we use the bearing basically to take a load. Okay, so to support a certain kind of a load. So the load will be supported through bearing and the end go to the ground, right? One typical kind of a load the bearing will support is called the radial load. So radial load is essentially the load perpendicular in the direction perpendicular, okay, to the shaft. Okay, that's a radial load. Okay, so the radial load, the drawing at here, sort of showing the distribution of the radial load along this bottom half of this bearing and here support. So it's not evenly distributed. There is a little nonlinearities at here in terms of the load distribution. Okay. The other typical one is called loading is a thrust load. So if there's axial force along the shaft, okay, axial force along the shaft, so the force will go through the shaft to the bearing and the bearing is going to be the some kind of thrust bearing, then the force through the bearing to the ground, right? So the bearing needs to be able to take the thrust loaded here, and that's sort of the loading distribution along the axial direction. Okay, again, it's not evenly distributed. Okay, yeah. So this is along the axial direction. Okay, axial direction, and in most cases, or most common cases, is you have a combined loading condition. So you have radial load and a thrust load. For example, if the shaft is carrying a helical gear or bevel gear, so you would have two kind of loading along the shaft. Then the bearing, okay, needs to be able to take care of both of these kind of loading. What we call is a combined load here. So when we design or when we select bearing, we basically will look at two different situations. One is when the bearing are subjected to purely radial load. Okay, so how do we select bearing under this situation? And the other situation is when the bearing is subjected to the radial load and thrust load together, or when it's subject to combined loading. Okay, so how do we select the bearing? Okay, so those are basically the two situations we're going to look at it. Okay, yeah. In terms of types of the roller bearing, there are different ways of classifying the bearings here. So this is one way of doing it. In terms of this, we basically saying whether five basic types that are here. Okay, basic type meaning ball bearing, cylindrical roller, taper roller. So why is it taper? Because the roller here has a little inclined angle at here. Okay, so that's basically called taper roller. Or you can have a spherical rollers. So spherical roller basically means the surface. If you look at the surface of the roller at here, it's a spherical surface. Okay, so that's why they call it spherical roller. Okay, yeah. Or you can have a needle rollers here. So the difference is basically the roller here is very, very thin, so it's like a needle. So this is the needle roller, and the needle roller, as we're going to see, is there's a variety of applications, particularly if you have a space restriction, and you also need the bearing to take a certain amount of high radial direction of load. Then you can use this needle roller bearing at here. Okay, so this is basically first type of classifying bearing. Five basic types at here. Okay. There are other way of classifying the bearing here is this way at here. Okay, so we call that radial ball bearing. So those are basically ball bearing at here. So what are the radial ball bearing? You can have deep groove, okay, ball bearing, single row. You can have angular contact, single row. Okay, so angular contact, we'll look at that, what angular contact is. You can have a double row, basically. You can have 4-point contact ball bearing. So those are ball bearing here, right? And this is classifying the bearing in terms of this one. Now it's saying roller bearing. So it's not a ball anymore. It's a roller at here. Okay. Yeah. So you have a cylindrical, needle, tapered, barrel roller, or spherical roller bearing. Okay. And now here, these two are the axial ball bearing. So axial ball bearing or axial roller bearing are mostly used basically to take the thrust loading, okay, to take thrust loading. So this is basically horizontal direction, and your shaft goes vertically, okay. Then one side of the shaft sitting on the top, let's say, then the shaft basically rotates, and this is your rotation side of the bearing there, okay. So you have this if you have an axial loading vertically, then this is going to be taking care of that. The axial loading. Okay, yeah. So if you look at the catalog, and basically every different manufacturers essentially have this kind of a bearing set here. Okay, yeah. So let's take a look at details of each one of the bearing in here. So first one, let's look at the ball bearing. Okay, so this animation in here is sort of showing you how to assemble a ball bearing in here. Those are basically the terminologies that we just mentioned in the previous slides. Ball bearing can take, okay, vertical load, which is basically radial load. At the same time, it can also take, okay, the thrust load in both directions. But mostly the deep groove ball bearing it's used for taking the radial loads. So the capacity for taking care of the thrust load is limited. Okay, so that's the ball bearing. If you're designing for a spur gear, then you better choose a ball bearing. Okay, so you basically you don't have a concern regarding the thrust load. You can also use a roller bearing though. Okay. Yeah. So how do we assemble it? There are two ways of assembling it. The first one here is called Conrad assembly. So what happens is you have the outer ring, so you put all the balls, okay, on the outer ring here, okay, and then you snap the inner ring into it and then press and squeeze the balls evenly around the inner ring. So this is called Conrad assembly radial ball bearing. And this one here is different, okay. This one here, basically they use a so-called filling slot. There is a little slot here, so you basically put the balls into it and each like that, right? Apparently, the second one here you can accommodate more a number of balls than this Conrad type of bearing right here. Okay. However, I mean, yeah, more balls meaning you can use it to take more axial load, right? But the disadvantage is what? Because of the slot right here, you have a stress concentration, right? Yeah, so that's basically the disadvantage. Okay, yeah. So you look at these balls here and the bearing here. So in general, you also need a seal or shield, okay, to basically cover the balls here. Normally there's some grease and lubrications inside this structure. Okay. So in terms of the protection and lubrication, that's a different topic. But in terms of the shields, okay, and there are basically different type of shielding. Shields you already mentioned is meaning that you have a metal piece that is here, and when you have a seal, basically you have a certain kind of plastic or rubric things at here. So this is a shield, okay, and there's a little gap right here. If you look at the catalog, generally they indicate what's the maximum or limiting speed, what's the operating temperatures, like that. Okay, those quantities. So for example, this one here, when you look at the catalog, they usually use a DDU as a sort of a subscript or a a suffix or something like that to indicate this is a double seal. Okay, this is actually what you call that. A touching type. So there's the lip maintain contact with the inner ring. So there's a little contact between this rubber and the inner ring at here. So which means it's pretty good seal, pretty good protection. The dirt won't go into this inner side here. However, because of touching at here, so that provides a little bit constraint or limitations on the maximum speed. Okay, yeah. So that's essentially sort of one way to identify what kind of a bearing you're looking for, what kind of a seal you're looking for here. Okay. VV is basically meaning it's a non-contact seal. Okay, non-contact at here. Because of non-contact, so it won't operate well if in a humid or watery kind of a situation. So water can go into it, right? Yeah. So angular contact ball bearing. So angular contact, it's the trick here is, okay, there is a ball here, and it's the contact between the ball and the groove, okay, or the outer ring, inner ring here, it maintains an angle at here, okay. So this angle here gives you so-called contact angle. So basically, the contact is actually not a surface-to-surface contact. The contact, if this is the ball right here, if you explode the contact here, then for the outer ring, okay, it's running out of ink here. The outer ring contact, okay, there is actually point contact here, okay, surface to surface, tangent to each other, and along the common normal, that's the direction of loading. Basically, that's how the force is going to be transmitted between this ball and the rings at here. Okay, so this angle at here, okay, this angle here is what we call the contact angle. Okay, yeah. The larger contact angle, then the angular ball bearing can support heavier thrust load. Okay. However, angular contact ball bearing for this kind of single row, it can only take one direction of a thrust load, which is the direction indicated by the arrow at here, right? If you apply the load in the opposite direction, guess what's going to happen? It's going to come apart, exactly, right? So essentially, when you use an angular ball bearing, you generally use a pair, okay, which basically in the opposite direction to take care of this axial loading in either direction. All right, yeah. So we'll see that shortly. Okay. So this kind of this diagram is sort of showing you a proper usage of angular ball bearing. As I said, if you don't use it properly, it's just going to come apart. Okay, yeah, falling apart. So when you use it, the angular ball bearing, you can use it as a pair. When you use it as a pair, there are two different ways of using it. The first one here is called back-to-back, and the one on the right is called face-to-face, right? Yeah. So back-to-back, essentially the extension of this contact angle, the line there, right, form you this kind of a triangle, okay? This kind of triangle. But in the face-to-face, the two contact lines, okay, intersect each other like this. Okay, so they form this kind of triangle here. Okay, this kind of triangle. So think about it. If you use when you use the first one compared to the second one, the A and the B there, okay, and you put that on the shaft, okay. So if the shaft is subjected to certain kind of a tilting moment, okay, certain kind of tilting moment. So guess which one will have a better capability of resisting the tilting moment? The A or B? The A, right? So A is basically, it's this structure. B is this structure, right? Overall, the loading. So if you have a tilting moment, imagine you have a big guys here, right? Stocky guys, and hard to tilt them. But this one is lame as me, you know, basically. It's easy for, right? But however, okay, so what in technical we call this is to provide a more rigid structure or stiff structure, okay, for the shaft, locating the shaft. And this one here, not as rigid as the other one, but however, it does provide a sort of a more flexibility, basically more flexibility in terms of alignment, okay, in terms of this second one here. So A is more mostly used, okay, than B though. Okay, so that's the angular ball bearing if you use it in a pair. Tandem, essentially pair it not in opposite direction, basically just two things arranged in the same direction. It basically gives you more capacity in taking the care of the thrust load, right? The tandem type of arrangement. Okay. So this is the sort of animation in here, as what I just said. The back-to-back compared to the face-to-face, right? So you have this kind of triangle here. So this is more rigid, and the top one is face-to-face, and that's less rigid and it's more flexible, right? Okay. Double row bearing. If your radial load is very high, and you can use this double row bearing, right? So carry higher and heavier radial load, and of course at the same time thrust load. Okay. But the only thing is the waist, right, will be bigger than single row. Okay. Yeah. However, compared to the tandem type of arrangement, the previous one there, it's more compact. Self-aligning double row bearing. So this is a situation essentially when the shaft is not so rigid, the shaft is a little bit flexible, and there is a tendency having a deflection on the shaft. Then the bearing, okay, is supposed to be able to take care of a certain amount of a misalignment. Basically, there's a certain amount of a deflection angle, okay, at the supporting location. So A better choice to take care of that problem with this self-aligning double row bearing here, okay, like these animations are showing over here, okay. As a matter of fact, every bearing has a certain amount of ability of taking care of this deflection or a little bit of a self-aligning. But this one here basically has a much better capacity because the structure, the top there, right? Yeah, that's double root bearing, self-aligning. Okay. Yeah. Thrust bearing, and this is what ball bearing here. This is what I showed you here. Basically, the shaft is going to be mounted vertically, okay, and the bearing will take care of the thrust load, which is along the shaft direction, right? But it doesn't take care of the radial load then, so you shouldn't subject it to a certain amount of radial load. If you do, then the whole thing will come apart again. Okay. Sometimes the manufacturer they have a little bit the so-called groove right here. Okay, so that basically provides a better ability of self-aligning here. So if the shaft has a little bit motion in this direction, then the bearing is able to take care of that. Okay, if it's very rigid, then you won't have that ability. Okay, so the lining capability. So this thing here, this surface is that spherical seating, that the structure over here. Okay. Cylindrical roller bearing. Okay, so this is not a ball anymore; it's a roller, right? It's a roller. When you look at the roller bearing, one thing that when you look at the catalog is, in general, they start with a letter instead of a number. Okay. So when it's a ball bearing, usually they start, let's say, 6 something, 5 something, or 3 something. But as a roller, they start with the N, it's a letter. Okay, it's a letter. The second letter, okay, if there's a second letter or not, indicates basically the type of the roller bearing here. Say, for example, if you have an N at here, so basically there is a groove, okay, and there are 2 flange, okay, at the inner ring at here, okay. And the top one here, there's nothing, just a flat. But it's NU, it's the other way around. So the flange is on the outer ring, and there's a flat here, right? Now, what does that to do? What does that basically? What does that thing they provide us here? Now, when you have a flange at here, so of course that roller cannot go anywhere, right? But if there's no flange at here, so imagine this, basically looking at this one here. So this outer ring will be sitting or be touching the gearbox or the casing, okay, housing of this gearbox, right? If there is certain kind of, let's say, thermal expansion of the shaft, okay, then what happens is the bearing at here will be able to provide certain kind of a capability of flexibility. Okay, a little bit the axial displacement is okay. Okay, so you go along this direction here. Is that good, right? This is what we call floating. So when you design a bearing, it's in general you have one side called fixed, the other side is called floating. So the floating capability basically is to take care of the thermal expansion, or basically because the shaft is expanding or shrinking. Okay, so that's basically the floating nature of capability. So if this side here, then it's floating here. So instead of this side is moving, so you can have a little bit of motion at this bottom here. Okay, at the bottom here. Okay, so that's floating. So here, if it's NF or NJ, and that's the structure corresponding to this notation at here. So NF meaning there is a groove, there is a flange at the top, but only one side. NJ, there is a flange at the bottom. There's only one side here, right? Yeah. Because this nature, so the floating is only in one direction, right? Not the other way. Okay. tapered roller bearing. So this roller here is essentially a cylindrical roller, right? And tapered, so the roller, okay, the two sides of the roller inclined. If you extend the sidelines of the roller, they will converge to one point. So that's what we call the tapered roller bearing. And the angle between this upper line at here and the horizontal rotational axis is, again, it's called angle of contact. Okay, it's called angle of contact. Tapered roller bearing compared to this cylindrical roller bearing is, cylindrical roller bearing depends on the type. You can take axial load maybe in two directions or maybe in one direction. It depends on the flange at here. Because the tapered roller bearing here, so it's able to take a much higher axial loading, okay, than that cylindrical roller bearing. However, you can only take the axial loading in one direction. In this case, so this direction at here, right? This direction. Okay. And the other fact is, the higher of this angle of contact, so the higher of this angle here, and this angle is the same as this angle here, okay, then you have a better axial loading capacity, okay, axial load capacity. Maximum in general, the angle of contact is like a 45 degree, okay. Yeah. Double row spherical bearing. So as we said, spherical bearing, roller bearing, basically the difference is it's not cylindrical, it's not a straight line. The two sides of the bearing, the surface, it's a spherical surface. So if you extend that surface, it's a sphere basically, right? It's a sphere. For the double row, it can take two directions of axial load, okay, and plus the radial load. Okay, the best quality or characteristic of the double row is basically it has a pretty good adjustment for misalignment here. So up to 2.5 degree, so that's pretty high. Okay. Needle bearing. So we said we look at the needle bearing in the previous slides. So you have a very small needles, okay, ruler at here, okay, and they arranged evenly in the inner ring. The needle bearing basically the best quality is to take high load carrying, so high radial load. Okay, that's a needle bearing. At the same time, okay, because the height is pretty compact, okay, in the needle bearing. So if you have a very tight situation, okay, in the design, and you want it to be able to want the bearing to take a very high radial load, then needle bearing is a better choice at here. Okay. Yeah. So bearing part numbering. Okay, bearing part numbering. So this is basically sort of a working experience. When you buy a bearing, you look at the catalog, right? So what does that number basically mean? Okay. Or when you call the representative, so what number should you give it to the rep over there, right? So there is a sort of a global standard in terms of numbering the bearing here. Okay, they have this IO standard, but there are slightly variation from manufacturer to different manufacturer, and that basically you need to look at the catalog. However, okay, in general, okay, you look at the bearing. Okay, just basically how many digits that you're looking at. So usually 5, but maybe 4. So there's 1 digit will be neglected here. But the first digits, okay, the first digits is what we call the type. Okay, the type of the bearing. So I'll show you in the next diagram. We'll see what the type means. Type basically means, is it a ball bearing? Is it a roller bearing? Is it something else? Okay. This one here, it could be there, it could be not. So in the bracket, meaning you may not have these digits here. But that's the digits called width series. Width. So how wide the bearing is. Okay, how wide the bearing is. And these digits here shows you is outside diameter, basically outer diameter series. So how tall the bearing is. Okay, so this number here tells you that trend. The last two digits basically tells you is the ball size, okay, the inner ring ball size of the bearing. Okay, yeah. And there is a quick way of checking this. So for example, 0.5, the ball size is basically going to be 0.5 times 5, so 25 millimeter. Okay, yeah. However, not always like that. If it's 0.1, 0.2, they have it's not times 5 though. Okay, not times 5. So let's look at couple of examples here, then I'll show you one diagram. So let's say if I have a 601. So 601 basically these digits, okay, this width digits here, it's not there. So it's a 60. Actually, it's actually these two both not here. 601 there. Okay. So the 1 here meaning is 1 millimeter, 2 millimeter, 9 means 9 millimeter like this. Okay. If 0, 0, 0, 1, 0, 2, 0, 3, they're up to 10, 12, 15, and 17. Then from 0, 4, you just multiply by 5. Okay, the 0, 4 would be 20, 0, 5 be 25, like that, right? Yeah. But if it's too high, okay, like this one I'm showing here. So if it's over 500 millimeter, so what you do is you can just you'll see that it's just simply just a 500 or 700, 800 like this. That's pretty big bearing basically. Okay, yeah. So this diagram, okay, kind of explain the numbering. Okay, this is from SKF catalog. Okay, so let's take a look at this diagram here. So what do we mean by first digits? Remember the first digits here, right? I showed you a 6 over there. What we call is the type. So this is basically the number coming from here. Okay, coming here. So 6, what's the 6? You look at the 6 here, that's basically a deep groove ball, single row ball bearing, right? That's 6. That's a type. If the first digit start with N, then you have a roller bearing, right? If it's 3, it's a tapered roller bearing. So that's the first digits. Second digits is this width. Okay, it's the width series here. Okay, both of them are called dimension series. Okay, dimension series. So what's the width? Width basically refer to this guy here. They call it sometimes they call it B, or sometimes they call it W. Okay, so that's this one here. Okay. So starting from 0 and up to 5, the higher the number, the wider the width. Okay, so if it's a 6, 5 compared to 6, 4, you will have a higher width for the 6, 5, right? Yeah. This digit set here is the outer diameter, basically coming from here. Okay, coming from here. And if look at this one here, basically if it's 8, which will have a smaller outside diameter than 9, and interestingly 9 has a smaller outer diameter than 0. So why is that? I have no idea. So they basically just did like that, right? Yeah. The last two digits are the ball dimension, as I just showed you an example, right? If it's a 0.1, meaning what? If it's 0.2, meaning what? 0.3, and 0.4, 20. 0.5, 25. So basically like that, right? Yeah. So the bearing, interestingly, is the catalog generally just give bearing, okay, just all in terms of SI unit, millimeter. Okay. So when you design, if it's a US unit, so basically our inch series, so we have to convert our inch to millimeter to find the suitable bearing though. All right, when we do the calculation. Okay, so the catalog in general, some catalog provides 2 columns. One is inch, millimeter. One is as inch. Okay, yeah. But the integer numbers are always in millimeter, not inches. Okay, yeah. So let's take another example here. If I have a bearing NU316, so what does that mean? So NU is the type, right? That's basically a roller bearing. Okay, 3, that's the outer diameter. This is basically a dimension series. 16, the ball size, 16 by 5, and that's 80 millimeter for the ball size. Okay. Yeah. So this diagram here kind of show you the combination. So when you have a combination of width series and dimension series, basically a combination of these two numbers here, okay, these two numbers, W and D. So let's take a look at this one here. It's a little confusing. Let's look at the first one. When the width is 0, okay, when the width is 0, your dimension series, the diameter series, basically your outer side diameter series can be 0, 1, 2, 3, 4, right? So combination 0, 0 has this kind of a characteristic. 0, 2 has this. So what does that mean? For the same width series, 0, 2 will have higher or basically will have a longer outer diameter. At the same time, your 0, 2 also has wider basically width at here compared to the 0, 0. All right, the same series. Okay, yeah. And if you compare 0, 0 with 1, 0, first 0 indicates the width. This 1 here indicates the width. So the second 0, 0, meaning they have the same outer side diameter here, right? Because the 1 is higher than 0, so this 1, 0 compared to 0, 0 has what? Has a wider width, right? Has a wider width, okay? So that's sort of a shortcut you can tell just based on the number of the bearing there, okay? A number bearing. Okay. This is just an example of a 0, 2. So this is basically 0, 2. We're looking at 0, 2 here. 10. That meaning is what? What does 10 tell you? What does the 10 give you at here? And that could be multiple choice here, right here, right? I have a 0, 2, 1, 0. And can you tell me what's the inner ball size? Which would be 50, right? Yeah. I have a 0, 2, 10. I have a 0, 3, 10. Which one has a higher width? A wider width? 0, 2 or 0, 3? 0, 3, right? Yeah, so that's what you can tell, okay? If I say I have a 0, 0, 10, I'd have a 0, 2, 10. So, wider width, okay? Yeah. Understand these numbering things here, okay? Yeah. As a matter of fact, I think this is it's important or not. As a mechanical engineer, I think when you go to work, particularly sort of industrial work which deal with the standard, the first few months I have a friend basically, and he said he did nothing except reading all the documents, get familiar with the standards. Okay, those thick documents there, right? Document meaning what's the numbering system, what's the standards, how do they basically specify things, right? You become an expert in these things here. So this is basically another diagram showing you the relationship between this numbering system here. Okay, yeah. So this is from NSK bearing catalog. Okay. Okay. So now here comes basically rolling bearing selection. Okay. We will look at in details, but in general, okay, when you select bearing, you need to take these things into consideration. What's the arrangement of the bearing, right? What's the direction, the magnitude, the external force? What's the life requirement? Basically, how many cycles do you need? Okay. What's the speed? Okay. What's the precision? And what kind of environment is working on? Do you need a seal or what kind of seal? Right? Do you need to compensate alignment or not? Right. So those things are the conditions in terms of selection of bearing. Okay. So selecting bearing meaning we had to do some calculation, then we go to the catalog, then we pick the right bearing, right? So what do we calculate? So the calculation is essentially based on the type of stress or loading the bearing is taking. So think about this: when you use a bearing, whether the bearing is under it's a thrust bearing or typical radial type of loading here, then the bearing will be subjected to a constant contact stress. So the balls will rotate inside the raceway. And if the radial load is this way here, then when the ball is underneath this raceway, it's going to be subject to the contact stress between the ball, the surface, and the raceway surface, right? So there's going to be a cyclic kind of a contact stress, okay? Yeah. When we deal with the gear, we design a gear, basically to calculate the contact stress on the gear surface, right? And when we calculate the contact stress, we use the AGMA equation, and that AGMA equation is derived based on the so-called Hertzen equation, the contact stress. Contact stress, considering there are two cylindrical objects in contact with each other, you derive the contact stress between that two, and that's your base equation for the AGMA, right? Yeah. But for bearing, the contact stress the physics is much more complicated than the simple Hertzen equation can explain. Okay, so when we're dealing with the bearings contact stress, it's not the Hertzen equation as used in the gear design. Okay, it's basically we're going to mostly use it's going to based on the certain kind of empirical equation or equation derived from experiment. Okay, to do the calculation, to do the selection. Okay, yeah. So here is a certain kind of a criteria for bearing. Okay, yeah. When you design for gear bearing, it's a design for fatigue, but the design equation is not exactly the kind of fatigue equation a modified Goodman like that we use. Okay, they basically have this so-called design principle. Okay, from this Timke company. Okay, this is a very famous company. Okay, and the criteria for the fatigue failure is this: spalling or pitting of an area of 0.01 inch square. So what is spalling? Spalling, basically, there's a little piece of metal chipped off on the surface of the raceway or on the ball. That's called spalling. So if that spalling area is 0.01 inch, then basically it's defined as a fatigue failure. Okay, yeah. So when it's subject to constant cyclic stress, the cyclic stress will eventually basically build up, and a certain amount of material probably will be chipping off. Right? I'll show you one picture next. The other standard, or the fatigue failure standard, developed by this American Bearing Manufacturing Association, it says this: when the first evidence of fatigue appears. Oh, look at that guy, so smart. What's the first evidence of fatigue appears? This one. So that's what they call the first evidence, right? Yeah. So how big that is, it didn't really say, right? It just gives you sort of a comparison set here. Okay. So that's defined by this so-called first evidence by the ABMA, like this, right? ABMA like this. So the whole idea is, okay, we need to calculate or certain things, okay, to prevent this kind of a fatigue failure from happening. However, okay, you also need to understand this, okay, even though the bearing develops this kind of a chip or spalling at here, that doesn't mean that, basically that doesn't mean like the bearing will stop working right away. Okay, right away here. So it'll probably still working. It can still provide good functionality. Okay, but it just in terms of the standard, okay, you would call that fatigue failure. Now, how do you know that there is such thing happens? Because this basically usually happens inside the bearing here, right? Unless you do a daily maintenance, you take everything apart, or not a daily, maybe regular maintenance, you can take a look at the visual observation. If you don't have that the advantage, then you can, based on the listening, basically, of the operation. If you hear some clunking noise, some kind of squeaking noise, okay, usually that means there's something wrong inside the bearing, right? Yeah. So when that when that shows up, you can also see that's your first evidence, basically, of a failure, right? Yeah. Okay, so enough of the talking in here, and let's get into the sort of the not the boring part, the mathematical part of how to select a bearing, do some calculations at here. Okay, yeah. So the first definition is called rating life. Okay, it's called rating life. Okay, rating life is always a concept corresponding to certain load. So this is a concept, okay, with respect to certain load. Okay, rating life. And when you look at the catalog or when you look at the standard, there's always a term called rating life. Okay, called rating life. So what is the rating life then? It's basically defined as number of revolutions. Okay, number of revolutions that 90%, okay, 90% of a group of bearings will achieve or exceed before failure. Before this failure criteria, okay, develops. Okay, so let me explain this here. So you subject a group of bearing, okay, every one of them, you do experiment, all of them subject to the same load F. Okay, then you observe, okay, basically each one of them, and record a number of cycles when the failure of criteria develops. What's the failure criteria? That basically the picture I showed you, the little spotting. Okay, yeah. So when that happens, you record this basically number of cycles. Then you look at it. Okay, so you look at that. What is the number of revolutions? So you look at all these lives here, right? What is the number of revolutions that 90% of that group, okay, will achieve or exceed? You see what I'm saying, right? So you have 10 of them maybe, but there are 9 of them are all above, let's say, I don't know, 5,000 cycles, right? So that's basically 5,000 cycles is this rated life or the rating life under the certain load F. Okay? So they're only basically, which means what? Which means you only have 10% of the group fail this test here, right? Only 10%. So you only look at this basically defines the 10% of this one here. So sometimes this rating life here, because 90%, we call that L10. So L10 life. So this is also used called L10 life. So basically mean 10% of the group, okay, will fail this will fail based on the failure criteria. Okay, L10 life. Some other catalog, they call it a B10 life. Okay. Okay, so just remember, right now the rating life, it's based on the reliability or probability at here. It's at 90%. Okay, it's 90%. So the next concept is basically we look at is the bearing load, okay, versus this rated life. Okay, versus rated life. The rated life is as well what we just said there. It's in the 90% or L10, right? It's a 90% or this L10 life. Okay, or L10 life. So here is what happens, and people do experiments, right? People do experiment, they subject each group of bearing with a certain amount of load. Then they do the experiment, they look at what's the L10 life for that group of load. So then they record the F and the corresponding L10. Give a different F, record a different L10. That makes sense? So they basically, in the end, they plot everything on the log. Okay, they plot everything on the log at here, and it turned out that this whole thing give us an approximate straight line at here. Okay, approximate straight line. All right, yeah. So basically, as I said, for example, if F equal to 500 pound force, okay, and it turned out that 90% of that group, okay, can exceed, if 90% of that group exceeds 5 times 10 to the power of 5 cycles, okay, then which means for this, under this load, your L10, okay, will be what? This one, okay, will be this, okay, because that's what it means here. So it's a straight line. So it's a straight line between log F and the log L, okay, log F and log L. And basically there's a slope at here, right, the slope. Then you can use a straight line to animate or to approximate, to fit all the data. That straight line equation, if you turn that back into normal, okay, not in terms of log, it's FL to the power of 1 over A equal a constant, okay, equal a constant here. Okay, so that's basically based on this diagram. Okay, so FL 1 over A equal a constant. Okay. Now, what is A then? The A is 3 for ball bearing, and A is 10/3 for roller bearing. Okay, roller bearing including cylindrical and taper. Okay, yeah. So that's A value. So is that good? Okay. So now comes to basically this next concept. Okay. It's called catalog loading, catalog load rating. Catalog load rating. So what is a catalog load rating? When you look at the catalog and you have a whole bunch of bearings and you have a certain kind of a so-called catalog loading, okay, value. So the catalog basically give you what the catalog give you the bearing is. They give you the rating life is 10 to the power of 6 number of cycles. It's 1 million cycles. Okay, so in catalog, the L10 is 10 to the power 6. Okay, 10 to the power 6. This is true for SKF. Okay, and most of the catalog. I think there's only one exception so far I've seen for the Timken. Remember the company said the Timken, they give you the 10 to the power 7. Okay, that's the rating life. Okay, yeah. So when you look in the catalog, they generally will state that, right? Whether it's a 10 to the power 6 or 7. But for SKF and other like NSK or NTN, they are all 10 to the power 6. So when you pick bearing, when you select a bearing, you can choose either from SKF or NSK or NTN, right? So they're all good. So L10 is 10 to the power 6. The corresponding loading, right? You see here, FL 1 to the power of A equal to constant. So the corresponding loading to this 10 to the power 6 is what we call the catalog load rating. Okay, the catalog load rating. Okay, is this catalog load rating. Catalog load rating is catalog load rating is rating as a C10. C10. Okay, so when you see C10, that meaning it's the catalog load rating corresponding to 1 million cycles. Okay, 1 million cycles. Okay, yeah. So sometimes the C10 is also called basic load rating. BLR. Okay, it's also called dynamic load, basic dynamic load. Okay, it's also called basic dynamic load. Okay, so later if you see all the names here, we probably will see the basic dynamic load more than anything else. Okay, so just basic dynamic load, that's basically the C10 at here. Okay, yeah. So then back to this basic question at here, basic equation here. So FL to the power 1 over A is a constant. So that means what? That means C10 times L10 to the power 1 over A equal to any other load F times L times 1 over A, right? Times 1 over A. Okay? Yeah. Is that correct? Yeah. So this one here, it's basically the very basic equation for calculation and in the end to make a decision in terms of selecting of a bearing here. So for example here, right? How do I select a bearing? When you select a bearing, basically you go to your catalog. You pick a bearing which has this rating value for the C10 that can take care of the loading F at here. That makes sense? Okay. So you have a shaft, and you design a shaft based on certain loading condition, right? So when you design the shaft, you have the supporting force at the loading at this bearing location. That's basically going to be the F for the bearing, right? F for the bearing. The L is going to be the life requirement for the bearing. Okay, so maybe the L is higher than 10 to the power 6, or maybe it's less. Who knows, right? Yeah. So based on this condition here, you can calculate a C10, basically what we call required value, right? Required. So that required meaning you go to the catalog, you find a bearing such that the bearing's C10 is higher than your calculated C10. Right, that's going to be the bearing. Okay, yeah. So that bearing will satisfy requirement basically. Okay, yeah. So we'll look at the details of this one here, but this is the fundamental equation here. Okay, every equation, everything essentially derived from here. What's the L here? Remember, L is a cycle. Basically, in this here, the unit for the L is a cycle, and the C10 can be pound force or kilonewton, okay, or F can be pound force kilonewton. So this is a cycle. Then, if the question didn't give you cycle, the question give you maybe, hey, I wanted to operate for a certain amount of hours at this speed, right? Then you can calculate the L, okay, based on the requirements here. So what you can do is basically, maybe you can calculate the life, okay, in hours times, okay, revolute per minute So number of revolution per minute, then times 60. So that'll give you the cycles. Okay, how many cycles do you get? Okay. So let's take a look at a quick example right here. So before we go along the quick example, here's a diagram from the textbook. The general question is, so when we design, how do we define the life basically, right? So here's the diagram, kind of recommended bearing life for the various classes of machinery. Okay, it's a little bit small, but those are basically recommended life here in terms of kilo hours. Okay. So let's look at an example right here. Okay, for example, so let's say if I have a ball bearing and the loading of the ball bearing, just sticking here. Alright, so giving a ball bearing from the catalog, the C10 value for the ball bearing is this. Okay, C10 is this, and L10, that's 10 to the power 6 for that catalog. Now the bearing is subjected to a load F, okay, equal 3,500 pound force. Then it asks the question is, how many number of cycles, or what's the design life for this bearing under this load at here, right? Under this load. Okay? Yeah. Before you do any calculation, right, establish the train right here. The rating, the C10 value, the basic dynamic load is 7,050. The current load is only 3,500, which is less than that. So what would you expect the design life? Would that be shorter than this 10 to the power 6, or be the longer than 10 to the power 6? Longer, right? Yeah. So basically, you go back to this equation right here. What do we know? We know this. We don't know this. We know this. We wanted this one here, right? We want this. And L, okay, equal to, let's say this is our L10 there, and then the times, okay, your F, you're actually times C10 divided by F, and then another 1 over A here to the power of A. Okay, so you basically solve this equation, right? Divide it to this side here and get rid of the 1 over A. Okay, take 1 to the power of A here. That's this equation. So as a matter of fact, that's the second kind of equation you may use in terms of this bearing calculations. Okay, so plug everything here. Your L is 8.17 times 10 to the power 6 number of cycles or revolutions. Okay, or revolutions. Okay, so that's your L10. Basically, this is your L10 life under this load F at here. So this is L10 life under the basic dynamic load at here, right? Yeah. Okay, so the second thing is, okay, maybe I can move this up a little bit here. Yeah, I'll move this concept up a little bit here. Now, up to this stage here, this is basically calculation based on this F. What you get here is another L10 life, right? Another L10 life. So in reality, you may not basically always deal with this 90% reliability. What's L10? L10 meaning 90% reliability, right? 90% of the bearing will exceed the required life. So in reality, if what you're dealing with is actually, oh, I just require maybe 80% or maybe higher, 95% reliability, all right? So then how do we deal with that situation then, right? How do we deal with that situation? So to deal with that situation here, there are two different options, okay? Two different options. I recommend this number one option, okay, which is from this table right here. So the number one option, okay, so I'll write it here. For okay, other reliability, okay, basically other than 90%, okay. Here's how you modify the equation here. Okay, here's to modify this equation. So this equation is modified. Option number one, okay, is this SKF, okay, life equation. This is not in the textbook, so I recommend this one here. It's relatively simpler. Okay. LKF one here is this. This is the formula. So L, if you calculating L, it's KR times C over KA FE to the power of A. So I'll explain it what KA is. Okay, but KR is a factor corresponding to different reliability. So here's a table here. Okay? This is basically, you see, for 90% KR is just 1, right? Just 1. If you have a different reliability, higher one, then KR taking the value from here. So if 95%, we're talking about L5 life, not L10 life. So 5% will fail, right? Yeah, they're much higher. L10 now, of course. So this is a KR. The C at here, that's basically C10. Okay. So C here, it's from the catalog. The FE, okay, I'll explain the FE. FE is so-called equivalent load. Okay, equivalent load. So what's FE? FE equal to this. FE equal to V times R, or just maybe V times F. V equal 1 for inner ring, 1.2 for outer ring. Okay, so that's V, and R is basically the resulted load. Okay, the resulted load at the bearing location. Okay, so what's the resulted load? If there's only one direction of load here, you know, there's just one direction, right? But maybe you have a two-plane bending. So maybe you have a loading here, you have a loading there. So you gotta have calculate basically the resulted load from the two planes here, right? That's the R resulted load. Well, we'll look at example for the R, right? So if it's inner ring, you just don't need to do anything. Outer ring, you multiply by 1.2. That's FE, right? Yeah. And the KA is called the loading factor. So generally, we'll take KA as 1, but let me see, do I have it here? Yeah. So this table here have a certain kind of recommended KA value, loading factor. So essentially, it's kind of type applications. Do you have impact or not? Light impact, moderate impact, precision. So that's sort of a general guidelines at here for the KA. All right? Yeah. So this equation here give you not L10 anymore, will give you either L5 or L4 or L1, right? Depends on the KR value. Okay? Yeah. Is that good? Yeah. So you might wonder is, Now, how come there's no value less than 90%? So basically, it's not recommended, right? It's the manufacturer is basically 90% there, so it's not recommended. You better just, you always want it to be to have a good design, right? So that's why. Okay, and that's option number 1. Okay, calculating the L, or maybe I'll write down another equation. So this is calculating the L at here, right? If we're not calculating L, if we're calculating the different ones, if we're calculating the C10 required, so if we're calculating as how much of the C10 do we need based on the given life, then the equation is written as this. So KAFE and L over KR and 1 over A. Okay. Yeah. And lastly, this this L at here. Okay, this L here, the unit of the L is actually not median number cycles anymore. This L is actually, let's see, if you calculate this one here, you end up with the 3.3. It's actually 3.3 times 10 to the power 6. Okay, this calculation here. So more precisely, this L here is the L already divided at 10 to the power 6, or the L10. Okay, from the catalog. Okay, yeah. So the L, let me write it down here. Okay, the L is in 10 to the power 6 revolutions. Okay, so when you calculate, so be careful with that. Okay? The results, the L, the unit is 10 to the power 6 revolutions. Okay, yeah. Any questions? All good? Yeah. So option number 2, it's the textbook option. Okay, it's textbook option. This one here, basically the calculation or the reliability is based on the probability concept. When you learn probability or statistics, we know that there are different kind of distributions, right? Distributions. The most common distribution is what? Is a normal distribution, right? Normal distribution. There's also t-distribution and something else, right? Yeah. And there's one distribution that's called a Weibull distribution, or Weibull distribution. So the following formula is basically based on this Weibull distribution at here. Okay, so here's a formula. Your C10 required equal Ka and Fe. Okay, then small xd over x naught plus theta minus x naught ln 1 over r capital D to the power 1 small b, and then to the power 1 small a. So this is more complicated basically than the SKF life equation. Okay, the SKF life equation. So what are these things here? X naught is 0.02, and theta minus x naught 4.439, small b 1.483. RD is the reliability, so you could have a 90% or 95%, right? So that's the RD there, RD. And XD is the life. So XD, this is a life in 10 to the power 6. Okay. So basically, this is the desired divided by L10. Okay. So L over L10. How much life do you need? Divided by 10 to the power 6. That's the XD. Okay, that's XD. So this is the second option. This is called this textbook from formula equation 11-7. Okay, the results are very close to each other. Yeah, very close. Slightly different, but very close. Okay, so which one do you want? It's up to you. Okay, it's up to you. Yeah. I would recommend the SKF. It's easier to calculate, right? Particularly in the exam setting. Okay? If design, it doesn't matter. Okay, you can use either one. Okay. So, in the end, actually we don't have time anymore. In the end, basically, we have two different kind of situations. Case number one. Okay, we have a design for radio, not a design. Well, let's call it calculation. So calculation for radio load only, and the second case is a calculation for combined load. Okay, for combined load. So that's the two different situations. If you're designing for spur gear, the first one will just satisfy the requirement. If you're designing helical gear, you would need the second one here. Okay? Yeah, so we'll talk about these two cases in the next lecture. Okay? Yeah. Oh, right. So Andrew, can you introduce open
Well, your L10 is 10 regardless. So yeah, so the L calculator, the XD is your actual your XD will be like 5.
Send me email, okay? And I'll forward that to the other one.
Can you say, for example, safety factors? So safety factors can be like a little higher.
Yes. I'm not saying you have to be exactly what I'm saying, right? You can or with a higher scale. Yeah. Compromise.